Now, it gets slightly more complicated than this, because what you have to start to understand is that the amount of force that we produce is not uniform across the length of the fibre. Let me explain. What you can see on the panel on the left is what we call the force or the length tension or the length force relationship. And what you can see is we've got sarcomere length on the x-axis, that is on the horizontal, and we've got the amount of force being produced on the y-axis. And what you'll notice is that we have what is almost an inverted U kind of relationship. That at the two extremes of length, so that is where the fibre is highly elongated, so that is at 0.5 on our graph, and where it is at 0.1 on our graph, almost no force is being produced at all. But you'll notice at points 2, 3 and 4, we've got almost 100% of the force being produced. So why is the amount of force being produced not uniform? Well, the answer lies in the panel on the right. And it lies in our understanding between the interaction between the actin and the myosin filaments. Remember that fundamentally what is happening is that you have got that three-dimensional structure that we were referring to, and you've got the actin filaments sliding or being pulled over the top of those myosin filaments. Let's just go back and see that in terms of the cartoon schematic. So just think about that carefully. Think about those the schematic in terms of the two-dimensional view where you can see the actin and myosin, and then look at it in the 3 dimensions with the hexagons of the actin sitting around the myosin filament. So what is happening is the actin filaments are being pulled, and they're being pulled across the myosin filaments. And this really does lend itself to our understanding of the length tension or the length force relationship. So if we look at point 5 and then look at on the graph and then look at image 5 in the figure on the right, you'll start to understand why there is almost no force being produced. In this example, the actin filaments, remember the actin filaments are connected, so these lines here are connected directly to the Z line of the Z disc. There is almost no interaction because the muscle has been, the sarcomeres and therefore the whole fibre has been pulled so far, elongated so far. There is no interaction between the actin and myosin filaments. And remember, the only way you generate force is by the myosin heads of the myosin filaments pulling on the actin filaments, on the actin structure. So there's no force. Whereas at point 1, you get the polar opposite. What has happened here is that the fibre has been so shortened that the Z discs come so close to each other that what's happening is that the actin filaments are sliding over the top of each other, or through each other, and therefore are preventing interaction between the myosin heads and the actin filaments. So the zero force is being produced. And this really explains a lot about what is happening, for example, when you're doing, say, a bicep curl. So if you imagine this is my bicep weight, and I have got my muscle, and I'm holding the weight. I'm just going to stand up so you can see it, but I'm holding the weight here, so I've got the muscle elongated. And that's a heavy weight, right? At that point there, it's really heavy because this ball's really heavy, but you've got that weight there. You know that it's really hard to get that moving, to generate the accelerational force. Why? Because there's almost no interaction between the actin and myosin filaments, because the muscle, therefore the fibres, therefore the sarcomeres, therefore the distance between the Z discs has pulled the actin filaments so far apart, there's almost no interaction between the actin and myosin filaments. When we go to this point here, so I'm now in a state of flexion and I want to now elongate, the same thing applies. To get that force going, to start generating the force, it's relatively hard to do it. Why? Because the muscle has been shortened, therefore the same thing applies. The fibres have been shortened, the distance between the Z discs within the sarcomeres has been shortened, therefore what you have is you have a lot of overlap with the actin filaments overlapping the myosin filaments to the point where you reduce the interaction between the actin and myosin filaments within the fibre. So almost no force is being produced. Whereas at points, particularly points 3 and 4, you're getting optimal interaction between the actin and myosin filaments. You're getting almost all the myosin heads interacting with the actin filaments. The less myosin heads that connect to the actin filament, less force is being produced. And that is the key. So when we're thinking about the amount of force we're producing, there is obviously an optimal point in the length that a muscle is held where you produce optimal force. You know that we're producing less force at the extremes of the range of motion. That's why bodybuilders tend to train over very short ranges of motion, because they recognize over those very short ranges of motion that is where the amount of hypertrophy is going to be developed, because they get the greatest interaction between the actin and the myosin filaments. And so this is the classic length-tension relationship of a muscle.